Here are solutions to test number 2 for ECE 461-661 control systems. This test looks at root locus and feedback. Now the first problem is, given this dynamic system, draw the root locus plot. So what you have is you have two zeros at -2 plus minus j2, poles at +1, -3, -1 plus minus j. So this is where the poles are. Didn't show the complex conjugate. What's given on the test is the blue lines. You add the rest. For real axis loci, that's when there's an odd number of poles and zeros to the right. So here's even, odd, even. So this is the real axis loci between -1 and -3. The breakaway points are where you leave the real axis. So this pole starts coming right, then splits apart. Here's one breakaway point. This one goes left. This one comes down. One goes left, one goes right. Here's the second breakaway point. There's the third breakaway point. The j-omega crossing is right here. You can find that numerically or just read it off the graph. The asymptote is the center of mass. So if I add up the poles at +1, -1, -1, -3, gives you 3, 4, 5, -4. The two zeros are also at -2, -2, -4. Zeros are opposite poles, so you subtract, gives you 0. 0 divided by the net difference, 2, gives you 0. So here's the asymptote intersect. The number of asymptotes have got 1, 2, 3, 4 poles, minus 2 zeros, gives you 2 extra poles. So the equation is 2 times theta is 180. Solve with theta. So the asymptotes are at ±90 degrees. And the hard one, calculating the approach angle and departure angle. Well, the approach angle is evaluate this a little bit thicker at s equals -2 plus j2 plus epsilon, like 10 to the -6. Evaluate it, and it's got to come up to 180 degrees. Evaluate this point just to the right. The angles of g of s adds up to, I didn't show it, adds up to -3.2 degrees. To get to 180, I've got to subtract another -176.8. That's this angle from 0. For the pole, I analyze instead at -1 plus j plus epsilon, and I've got to get to 180. Well, when I do that, to find the departure angle, I analyze at -1 plus j plus epsilon, and when I do that, I get +117 degrees. So the pole has to add 63 degrees to get to 180. Since it's a pole, I subtract, so I need a double negative. This is actually -63 degrees, so when I divide, it's +63 degrees, gives you 180. So that'd be the approach angle, or departure angle. Problem 2 is root locus and gain compensation. First, I want to get 40% overshoot. So if we go to the second order damping curves, it's between 0.2 and 0.3, closer to 0.3. So estimating about 0.28 would be the damping ratio. Take the arc cosine, it's 73 degrees. So here's your damping line. It leaves the origin at 73 degrees, and to draw that, take the tangent. The tangent of 73 degrees is 3.8, so over 1, up 3.8, over another 1, up 3.8. There's your angle. What I'm looking for is this point. Where does the damping line cross the root locus plot? It crosses at -0.4 plus minus j 1.4. At any point on the root locus, g times k is -1. So analyze this at that point, and you get about 0.2. Pick k to make the gain 1. I need a gain of 4.5. Finally, the error constant is the DC gain. What is k of s times g of s as s goes to 0? So as s goes to 0, I find g of s times k of s as s goes to 0, which is just 4.5. Multiply the two together, and you get 3.34. Problem number 3. Now, number 3 actually has multiple solutions. I start with this system. I want to come up with a closed loop system that has no error per step input and places the closed loop dominant pole at -1 plus minus J3. So currently this is a type 0 system. I know right away I've got to add a pole at s equals 0 to make it type 1. So add a pole right here. If I do that, these poles come together and it's too slow. So cancel the first pole at 0.4. This is going to cause trouble too, still too slow. Cancel the pole at 2. And if I analyze this right now, it's still past 180, so I actually need to cancel the third pole, s plus 4. If I add 3 poles, or 3 zeros, I need to add 3 poles. So one way to do it is, I don't know where these poles belong, I'll just put them at the same spot. Now to find A and find K. Once you find the form of K of S, then I know what G times K is. Analyze what I know. I don't know K, don't know A, analyze everything else. The whole angle's got to add up to 180. It's short, which is good. That means A, each one contributes 7 degrees for a total of 14 degrees. To find A then, it's some trig. Here's this side is 3. This side right here is 3 over the tangent of 7 degrees plus 1. So A is 25.39. To find K, any point on the root locus, G times K is -1. Analyzing at my design point, angle's 180. That's good. That says I did it right. Gain's wrong. Pick K to make the gain 1. So when you're done, here's K of S. And there are other solutions. But basically, as long as the closed loop dominant pole is at -1 plus J3, meaning G times K is 1 at 180 degrees, it's a valid solution. Finally, find R and C to implement K of S. Now this is a compensator, we don't know the form, but I can do some algebra, rearrange it, and this gives me a lead compensator and here's my PI. So for the lead compensator, I've got 3 constraints, 4 degrees of freedom. Somebody's arbitrary. I like letting this one be 1 meg. As s goes to infinity, this becomes 10. So pick this resistor so the gain is 10. That's 100K. This is a 3.5 to 1 ratio, so this is 2.5 times bigger. Another way to do that, as s goes to 0, this is 20 over 7. The total resistance is 350K, give you a gain of 20 over 7. Here's 100K, there's the remainder. Finally, the zeros at -2, 1 over RC equals 2, gives you C. For the PI compensator, I've got 2 constraints, 3 degrees of freedom. I like letting this one be 1 meg. As s goes to infinity, the gain is 5, so this is 1/5 of a meg. And then the RC time constant is 6. And that is test number 2 for ECE 461.